start. So yesterday, so this is all, I remind you, about physical descriptions of biological active processes and systems. And yesterday, I gave maybe a little too long an introduction to the biology of the cytoskeleton. And we also started to look at possible physical descriptions. I mentioned that there's the possibility, of course, to do simulations, statistical simulations, where you more or less faithfully try to represent the actions of various components of the cytoskeleton. It was also very briefly talking about kinematic approach, where you really think about distributions, and this you can do in easy cases. What I would like to do today is to talk about phenomenological approach, because we have seen that all these descriptions that approaches that I was mentioning before maybe have some troubles to capture all the diversity and the features of the cytoskeleton. So today will be a purely phenomenological approach, what is then also sometimes called as the gel theory. I think this is what I call the fluid theory, because everything I'm going to talk about will be purely viscous and nothing more viscoelastic effect. And what I will use here is the framework of non-equilibrium thermodynamics, and I expect that there will be some discussions about this approach at some point too. So what we're going to deal with only so-called hydrodynamic modes. So we are going to be interested only in those deviations from thermodynamic equilibrium where you have long length scales, and that these perturbations they decay on long time scales. And what I mean by this is that when you have a characteristic length scale of this perturbation called lambda, then the time to relax this would go like lambda squared. And there are two main origins of such hydrodynamic modes. One would be conservation laws, and the other is broken continuous symmetries. And we are going to talk about the second part later. Remember from yesterday that the actin filaments, they have first of all, elongated objects, and they have a plus end and a minus end. So when you align them, they can give rise to macroscopic polar order. And this will be an example of a broken continuous symmetry. But first, I would like to start with conservation laws. There are a few that we're going to consider. And the first one will be just mass conservation. So if rho is the mass density, then we have that the partial derivative would change in time. So the density would change in time. That's according to some current. And the current is given here by rho times the velocity field v. So what you see here immediately is that I have only one density. So what I'm going to do is I'm going to use a one component description of the system. This again does probably not do justice to the cytoskeleton and all its beauty, but again, for pedagogical purposes, the simplest case we're going to look at, and we can discuss either today or in 2 days what changes when you have a multi-component description, and maybe how you can justify one component description in some circumstances. Okay, so rho the mass density and v is the velocity. The next conserved quantity that we're going to look at and we're going to consider is momentum. So I will introduce the momentum density G, which is just given by rho times v, nothing in particular here. And then write down the equation, the continuity equation that corresponds to it. We'll do it in the following way. And I will comment on the second. So again, we have the same form as before, the partial derivative of our density. Then we have the divergence of a current. And this is why I use actually the notation components here, because after time, yeah, here tensors, and then it's a little bit complicated for me notationally to denote it in some other way. So here, what we assume is this Einstein convention that beta is an index. If it, all the Greek indices, they get twice in the sum over them, and then so here it would implicitly have a sum from beta from 1 to 3. Let's say if you're in 3 dimensions, and this will be applied all the time. Sigma total. This tensor is just the total momentum flux density. And it's the same as total stress. And then we have possibly the density of external forces. We see in some circumstances we'll consider that or not. Maybe I should remind you here that here I've set the source and sink terms equal to 0. In general, this would not be the case. So it's a little bit inconsistent, I understand. But here I just wrote a general expression. Here I could also add just in a formal way all the source and sink terms corresponding to polymerization or assembly of actin filaments or the actin-myosin network, and also this is something. Yes.
It's like this. So yesterday you wrote the question for rho plus rho minus.
Yes.
And I guess you ignored the velocity field. And
Yes. So
right now you are including that.
yes. So here now we will really describe this one as one component where you have the velocity field included. Yesterday I was just describing the there was still a current of the density, but there was no velocity of the surrounding fluid that we consider.
But when is that good description? Because then I would imagine that.
Okay, so I don't want to talk about that too much, but so the description yesterday, I think you can think of it being a description when filaments move close to a surface, and all the fluid that is surrounding this is more or less immobile because it's immobilized by the surface. That's very vague. There's no.
So
Yes.
again, can we this rho is the density of the fluid,
Of the active fluid. Yeah.
active fluid, but the filaments are coupled.
So exactly. So this active fluid contains the actin filament, the molecular motors, the crosslinkers, the surrounding buffer. It contains all the chemical species that are necessary to make the system work.
Oh, so I guess if I can rephrase this question, is there a possible way to go from the description from yesterday to the description today in a systematic course? I think that might be the question that the rigorous.
Yeah. So you can go to a coarse-grained version of the system that we saw yesterday, and if you tweak it a little, you can bring it into the form that you have.
Now, being a multi-component fluid, though, using like a continuity equation for the overall fluid when you've got multiple components, could you comment on that?
So you can
have relative,
so everything,
velocity, etc.
So everything that I'm doing now, you could do it also for multiple component system. People have done that to various degrees. In that case, this one would be the total mass density, and you would here have the center of mass velocity, and then you would have diffusive fluxes, as you will see later, that come around it. In principle, you can do all that. But
Can you comment on the validity of the single component approach?
so here it's valid because it's pedagogical, so it's the same thing as we do. And again, so in case when you are close to a surface where you mobilize the background fluid, so I think there you can reasonably assume that the point component description for the optimized network is
Okay, you go into the more.
If you then
You're gonna have some oral aspect about it.
exactly. So there then, but it also depends then also on the situation. Yeah, on the system, on the phenomena that you want to look at. So so for the time being, let's just keep with this to illustrate the approach, and we can discuss generalizations afterwards. And then in any case, you have to check afterwards whether your description is really appropriate for your system by comparing to experiments. And I think that's the point where the most work still is needed. Yeah, lots of interesting formal results or purely computational results about all these active gels, but then the real comparison to experiments, I think there are still lots of work is done, in particular in combination with experimentalists to get parameters and to compare the quantitatively. Any other questions?
There's if you're a source term in a mass confirmation equation, you also have an certain moment, right? SPL.
Well, you have the external force.
That's in the F.
That's in the F, yeah. So that's the only source of momentum that you have. Okay. Good. Then there's another conservation that I would like to mention, and that is that of angular momentum. I would like to consider this explicitly because we are going to look at systems that have this orientation degree of freedom. And these anisotropies that come with it, they will add some additional terms that are really important in the following. So I will write first it down. I will write down angular momentum density as a two tensor. Then we have the total angular momentum flux density. And then now we also have to have source terms and sink terms. So one is just coming from the application of the external forces, which can generate torques. And then there might be, in principle, also some additional torques that so that might I think I will not really consider this, but in principle you can think about applying external torques on the local level also to the system. So here L alpha beta with the rho alpha times d beta minus rho beta times d alpha and total alpha beta 1. So this would be a 3 times, and this would be a total angular momentum flux density. And as you can see, since L alpha beta is antisymmetric in the first two indices, and total is also antisymmetric alpha and beta. Good. So far so good. In the way that I'm developing the things here, there is a relation. So we can write down the total angular momentum flux density in a certain form. We can separate it as we did for the angular momentum source, also in two parts, just to get the indices right. Look like this. The total density can be written in one part plus a part that resides from the total momentum flux density. There's one part that comes from the total momentum flux density, and then there's another part that really accounts for molecular anisotropy that are not necessarily by the total momentum flux density by the total stress. Oh, so that is in 2D and 3D, whatever you want. I mean, 1D doesn't make sense, but otherwise it's okay. But you have 3 indices because you have to take here the divergence. So if you contract with the divergence operator, you still have to have 2 indices. So that's the formal argument. But so the physical argument would be that here angular momentum, I write it as a 2 tensor, and you can transport it in all 3 directions. This gives you this third index. Right, so like for the stress, you have your momentum flux, which is itself a vector. You transport it in all 3 directions, let's say. So this gives you these 2 indices.
That is a maximum.
And now, well, you could also write it as extra vector. Yeah. But still, I mean, so angular momentum here, so as I write it as a 2 tensor, and as you can transport it in all spatial directions, you get it. Yeah, it's a little bit of index gymnastics. I agree. I don't think one has to be careful not to lose any. And still, I think it's the cleanest way to write things.
That specifically gives out a symmetric form.
So there's okay. So that. So there's a relation actually between the antisymmetric part of the total stress tensor, which is related to this one, and that is the factor of 1/2. And it's related to this part that comes really from the molecular anisotropies. So in all what I'm doing, I'm going to maintain this antisymmetric part. In principle, you could also equivalently use a different form of the stress tensor where you get rid of the antisymmetric part. It's all resolved by Martin Parodi and Bertrand. But again, let's keep with this one. And you'll see in the end if you want to make modifications on good. And then energy conservation we're not going to talk about for 2 reasons. So first of all, most cellular systems are really at constant temperature.
So sorry, but what is this?
Oh, so it's antisymmetric. Sorry.
Oh, yeah, okay.
All right. Thank you. Was I just saying? Energy, exactly. So we're not going to consider energy conservation because things are happening at constant temperature. I think it would be interesting to take this into account at some point. And as far as I know, nobody has done so for the time being. So, for example, if you let your muscle work, which is an active gel after all, right, you see that it's heating up. So these effects could be interesting. But as I said, as far as I know, nobody has looked at that.
For normal fluid, I will write equations for density, momentum, and let's say energy, and that would form a conflict. And I wouldn't worry about the angular momentum.
Yeah, so I wonder about angular momentum because there's another source of a conservation of a hydrodynamic mode, and that's the molecular anisotropy, let's call it. So there will be a field P, the polarization field, which accounts for the fact that if I align all my actin filaments, I'll be able to generate macroscopically orientational order. And in order to account for that in a correct way, I better consider also angular momentum conservation. Because then you will see that naturally all the terms that are necessary will come out. And there will be modifications, for example, it will be the hydrostatic pressure that result from it. So for the time being, it does not appear at all. For the time being, it does not appear at all. That's now another field, and we will have to write down also an equation for the time evolution of this field. And how to do that.
But right now, the angular momentum doesn't look like independent.
For the time being, well, there is this part here, this M, which actually will be related to the field, to the polarity field, the polarization field, sorry. Okay. And you will also see that eventually also the total stress will depend actually on the polarization field, as you will see.
I should just say generally the one people write down dynamics of the distance. This is often how one way of writing down the distance. This is how you get the the dynamics.
Yes. So exactly what I'm doing right now is exactly writing down the equations for polar liquid crystal. Maybe that's also a good point to make a remark. So when I think about the polarization field, then there was mentioned, so you might have actin filaments that are all aligned. It gives rise to polar order, but you might also have an alignment of the actin filaments where you have, let's say, as many pointing upwards as downwards. So you would still have some orientational order, but you will not have any polar order anymore. So this is what we would call a mimetic state. And this you could describe to a large extent also by a vector, which would then be rather director. We would have to make sure that all the equations remain invariant and they're changing the sign of this one, or you could use a two tensor in order to describe this mimetic order. So in fact, these two systems, or these two systems, they have a lot of things in common. However, there are two places at which they really differ. One is at surfaces, because there it might really make a difference whether you have polar order or mimetic order, and also at destination points, also known as topological defects. Right. So because if you consider, for example, a mimetic system where you only have an alignment, so I don't put any arrowhead anywhere, and let's say we have a defect here, then for example, we could have something of this sort, so it's a very poor means version of a plus 1/2 defect. Whereas with a polar system, you could never have such a defect, because if I add my dashes here, then you would see that if I make a full turn, I will not be compatible. So the only thing that the lowest order defects I can have would be the plus 1 defect. That would, for example, look like this in the polar system. So here at that case, you will see that there's a really difference between the mimetics and the polar field. Good. Okay. So now these are the quantities that I'm willing to consider. And as Tani mentioned already, this would be the same thing if you just wanted to describe a, let's say, a polar liquid crystal. Now the next question is, there are some quantities that are obviously not specified. There's the velocity field here, but there's in particular also the total momentum flux and the total angular momentum flux that are specified. And I have not written down anything for the time distribution of P, which is not following the conservation law, because there's no reason why the polarization should be conserved. Right? So the question is now, how do we get expressions for these fluxes? And this is where I would like to use non-equilibrium thermodynamics. So there, the idea is that you place yourself close to thermodynamic equilibrium and perturb around this equilibrium state. And from that, and there's a procedure that I'm going to follow afterwards in order to get to expressions, what we call the constitutive equations for the various currents. Now, the way that we expand around the thermodynamic equilibrium is a little bit bizarre, I would say. Maybe some people will disagree, but I think it's still strange, because what you assume is that you subdivide your space in your mind into, let's say, small volume elements. while small volume elements, these are volume elements in which such that each volume element at all times is at equilibrium. Now, adjacent volume elements can be in different equilibria. So you will still have a possibility to then change the equilibrium states by having mass, energy, whatever exchange between the neighboring volume elements. And this is why we, in an intuitive way, at least need to consider these hydrodynamic modes, because this means that really it makes sense, at least on the scale of the perturbations that you look at, to consider smaller spatial scales to be at equilibrium, so smaller than the perturbations that you look at. And they also evolve in a time that is slow enough such at all times I can consider these volume elements to be at equilibrium. So I'm not sure that one can make this approximation really mathematically rigorous. Would be interesting to see if somebody can do that. Yeah, local equilibrium, yeah. I would be interested at some point to learning if one can really make this and put this on solid mathematical grounds. But intuitively, that's maybe the worst word to use in this context, but I think it's okay for me to accept that I can really look only at so large length scale and slow variations of my field that locally it's always to a good approximation at equilibrium. If we accept that, then we can go on and can use concepts from thermodynamics. Namely, we can use for each of our volume elements the free energy, because it's always at equilibrium, so there's no problem to write that down. And then we go to the continuum limit, magic, and write down everything in terms of density. So what we will use is going to be a free energy density. And so this will be the central object in order to get in a sort of systematic way to get to my equations, to my constitutive equations that will express eventually all my fluxes in terms of the quantities that we have already introduced. But I think conceptually this is the crucial part. And it should be discussed. Okay, so what do I write down for my free energy? So this will have two contributions. So I will add to my free energy density one part that takes into account kinetic energy. So again, the sum over alpha, so this is just the kinetic energy density. And then I will have an internal free energy density, and this I would say depends on SPL low, also depends on P. If you want, you can explicitly also let it depend on the derivatives of P. So now having this, the first thing I would like to briefly mention is that what you know from equilibrium, namely the pressure, now has to be generalized. And this is due to these molecular anisotropes. And you can see that, I think, at least in an intuitive way, that if you consider the following situation, it is sometimes called the magic spiral, where you have your orientation field, you anchor it such that it's parallel to the outer rim and it's perpendicular to the inner rim. And so what you will have is a change in the polarization field. And what we will see later is that this configuration is associated with a momentum flux due to the antisymmetric part of the stress tensor. Since this is equilibrium, and since you don't want to have any angular momentum flux here in total, right? Because at equilibrium all the fluxes should vanish. You need to have some part that compensates, and that will be just exactly this part. And only in this way you would be able to get right in the correct equilibrium state. And so this boils down to something that the hydrostatic pressure has to be generalized, and this would be what people call the Ericsson stress. And let me just write the expression down. I will not divide it. You can get it by considering a finite volume containing our fluid, and then you change the volume. And then if you look at the response of the system, so the change in free energy of the system to the volume change, then you can infer from that this Ericsson stress, which I will denote by a subscript E, and the components will be, so there will be one part that will be just the let's say hydro pressure part, which I will write down in the following way. So rho divided by m, I would say second word is so m would be the molecular mass, or a molecular mass. So remember, we are in a one component situation. So this molecular mass would be the same for all our particles. And in this way, I can relate the mass density to a particle number density, which I will call m. And if you do that in this way, this mu will be the usual chemical potential. So it's again something that might be a little bit confusing. So we use interchangeably either the mass density or the particle number density, and they're related by a factor which I interpret as molecular mass. And this allows me to write the first part in the way as I did. But then there's a second part, there's a minus sign. Yes, there's a minus sign, which would be not the no. So I'm deriving f with respect to derivatives of t, of the t. And this, I have no way to argue in a hand-waving way why this is the correct expression. If somebody has an intuitive way of saying that, please speak up. Formally, I can get it. But it just shows you that the hydrostatic pressure has to be extended by magnetic density on gradients of the polarization field, and this is what helps us to get this situation right.
So it's really at naught in the first expression.
Well, that should be at naught, yes. Thank you. Okay, if you have swallowed all this, then we can continue with the recipe that people use in equilibrium thermodynamics in order to get our expressions, our constitutive relation. And what we do for that is we at entropy production. And since so first of all, I'm allowed to use entropy. So even though I'm in a non-equilibrium system, since locally I'm always in equilibrium, there's no discussion that I can use entropy. Even though it's not clear whether entropy is really only confined to the equilibrium concept. If you just count microstates and you have macrostates, then probably this is something that goes for all systems, whether they are in or outside equilibrium. Again, something certainly worth of discussion, but here there's no problem. So what I'm going to do is I'm going to write down the entropy production to the dissipation rate, which would be theta, and multiply it by t. And in this way, you can just say that this is the time derivative of the total of the total free energy in our system. And this holds if I assume that I have no, if I do not do any work on my system, then if the previous, let's say, infinitely extended system, I don't have any boundaries to worry about. And if I do this, then this involves a little bit of computation. Then I can write the entropy production in the following way. So minus signs without an integral over space. As I said, I'm considering that a system which is infinite. We just look at the bulk equations, and then I see that there are two terms that come up in this system. So there's one term that we will call sigma alpha beta v alpha beta. Let's start with the simple term, the alpha beta. It's just the symmetric part of the velocity gradient. The sigma alpha beta, I mind you, there's no E and there's no total and anything, because this is the what we call the deviatory. Right? And in fact, it's only the symmetric part of it. And so explicitly, we can write this in the following way. So I take the total stress. From the total stress, I subtract the antisymmetric part. And from this now symmetric part of the total stress, there are two things I have to subtract. One is the Ericsson stress, and also on this one only the symmetric part. I subtract from the Ericsson stress its antisymmetric part, and then I also have to subtract the Rayleigh stress, which is just rho and the alpha. And so this will give me then, so this is already a symmetric part, so there's no interpretation necessary here. So this gives me the symmetric part of the stress that we will have in addition to the Ericsson stress, so the generalization, let's say, of the pressure. And also there's this part that really comes from the kinetic. This later we will neglect in any case, because essentially all the, maybe not all, but a large portion of biological processes flows happen really at a Reynolds number. So this will vanish in some place in any case. I cannot do the derivation though by starting in the Reynolds number case. I always have to first consider the kinetic energy and then afterwards go to the limit where I can neglect that.
So in the top equation on the right, you just said, you're assuming you're not doing the work.
Yes.
Yeah. So again, that is presumably with the idea of a one component in compressible fluid, right? Which you can.
So I think that anything about incompressibility, but
Well, but incompressibility, I think is basically a certain.
I mean, the first example that I will not take today, but what I wanted today will be incompressible as well.
Right, and so that's another area where one need to relax, and if you go to a multi-component system, because you can have relative compression.
Yeah, okay, so
At least.
yes, sure. And you can have internal change transformation of various kinds of energy, right? But what I'm talking about here is that you don't do any external work on it. Internally, of course, things can happen.
Right, but if I've got a compressible, you know, okay. And sort of related to that, I assume this Ericsson stress, I haven't gone through that, but that presumably thermotropic, crystal, not monotropic, right? Where you do that.
No, this should, No, this one also works in the presence of.
Generalized rounding.
Yes, so because this is really just look at all the effects of volume change. I should recheck, but as far as I'm aware, there's no restriction here. Yes,
Right now, you're just looking at non-active.
we come to the active part in two terms.
But right now, it's everything non-active.
For the time being, this is.
That's happening. In the state, we just get it in, I don't know. Still explode, for example. Yeah.
Okay, so the. Okay, so that, this was hard, not impossible to get. So what I just wanted to motivate why there need to be additional components to the to hydrostatic stress. And for that, I wanted to look at this situation where you have two concentric cylinders, let's say, take a 2D version of it. And let's say they are freely turnable. What you will see later is that, or what you see is that in the stress, there will be a component that comes from gradients in the polarization vector. These gradients in the polarization vector, so this means they will generate a torque. And this torque, if it were not compensated by any other torque, would make your system turn, which in equilibrium you cannot have. So you know from that there must be some compensating angular momentum flux to that one. And this is contained in this M expression and comes from the Ericsson stress. So now the next part that we get is the d by dt alpha and h alpha. So this is now the place where the polarization finally appears explicitly. So the d by dt would be the convective co-rotational derivative of a vector. It would be a d by dt but to be alpha, let's see this. Alpha plus and omega alpha beta. In beta, where omega here is now the antisymmetric part of the velocity stress tensor. And this is something I find nice. So just by doing the computation, you get the appearance of the convective correlational derivative immediately. So there's nothing that you have to argue outside of this language.
You got missing P alpha.
Sorry. Thank you.
It's also not
Yeah, I have one for
symmetric part of the velocity gradient, which has a arbitrary coefficient, which is the same.
Yeah, but okay, so from this computation, you only get at this part. There will be another part linking, so the flow line part with foundation.
So that's separate from that.
That's separate from this one. Okay.
This is just co-rotation.
Yeah.
This is called co-rotation.
I know what this is.
Yeah, okay, good. Well, and this is just, well, this requires this one. You just require this to be traditional judgment there.
I don't require anything. I'm just.
But I think that's really no, but this makes sure that.
But there will be additional terms here, right? I mean, this is not everything. I'm just explaining what this derivative is. I'm not yet explaining how to express this derivative in terms of the other one.
But the split parameter does actually hint. Okay, thank you. Anyway, just carry on.
Yeah.
See where it comes in.
So then the next thing is to say that's how we typically call it molecular field and the partial derivative of f. So and so for the time being, as Abhishek has said, there's nothing active about this. And now at some point I have to put up an Fisher as we can learn. So we have to create something that makes it active. And in principle, I was talking yesterday about that the processes that make our system active are driven by ATP hydrolysis. So this was this protein that has this phosphate group. When you cleave off this phosphate group, you liberate chemical energy. And in principle, what I should have done, and this is why this one component description is a little bit weird, we should have also, I should have at least also accounted for the density of ATP and its hydrolysis product at least. What I'm implicitly assuming is that these fields, I will maintain them stationary. So whenever I consume ATP, it's immediately replenished by some magic. But I still have a contribution to the enthalpy production from this reaction. And this will be the rate of ATP hydrolysis times the difference in chemical potential of ATP and its hydrolysis products. So R would be the ATP hydrolysis rate. And delta mu would be the difference in chemical potential of ATP, and inorganic phosphate. Remember that ATP is converted into ADP, API, and chemical energy. And this form of the entropy production rate I will now take as the basis in order to get phenomenological expressions for the various terms that are identified before, as well as for the temperature change of our polarization field.
And I guess just make a comment. I mean, this is all based on assuming that the alpha beta is small, H alpha is small, and delta V is small.
It's all based on this assumption that we're close to thermodynamic equilibrium.
Yes, usually very small.
What?
If you don't say small compared to what?
Exactly. Yes.
Yeah, big, yeah, well. Small compared to the other things in the system.
It's something else.
Yes, exactly.
Okay, but what is interesting now here is that what we see appearing is the sigma alpha beta, which is part of our stress tensor, and we see the rate of change of the alpha appearing. And so these quantities that we still don't know how to express them in terms of all the other quantities, they appear here. And if I had written down the continuity equation for ATP, ADP, API explicitly, we would also have this rate of ATP hydrolysis during the explicit one. So those quantities that I still don't know, they appear here explicitly. And you see that they always appear with a partner. And what we're going to assume, and that's now the main thing of thermodynamics, is to say that we are going to interpret these as what people would call generalized thermodynamic fluxes. And the origin of these fluxes are generalized thermodynamic forces, which are just the partners with which I have conjugated them to this computation. Now, there are lots of things to say about this, so maybe I just use this and then we can discuss, but not too long because Spoda wants to talk. Let me just finish by saying what I'm going to do now is I'm going to use the expression So these would be my generalized thermodynamic fluxes. In the principle also are, even though I already mentioned that I'm not really interested in that one. And then we have the thermodynamic forces. And they would be in this case the alpha beta, with the H alpha, and it would be delta mu. And now what I'm going to do is I'm going to express these quantities in terms of these quantities. Since I do not know in general what their relation is, I will just do an expansion around an equilibrium state where these are all zero. And these are all zero when these are all zero. And so what I will do is in this expansion, I will take only into account the lowest order terms, which are the linear terms. And well, often it's written in the following way. So I'm going to the linear term here. This is assuming already incompressibility. Otherwise, there would also I would have to distinguish between shear viscosity and bulk viscosity. So eta is the viscosity that you want to know. And now there are a few terms that come from the coupling to the other quantities. So I would like to first talk about the terms that already couple by things to my ATP hydrolysis, so to delta mu, because these will be the so-called active components of the stress, and there are a number of them. So this one is a tensor of order 2. So there will be a theta prime or delta alpha beta delta mu. So this would be the only way how to couple this delta mu to my stress in case we haven't had an isotopic system. But now we have this molecular anisotropy, we have the p vectors. And so I'm going to, in some sense, deviate from my linearity. We will use them to generate more terms. So there would be one that is beta bar, p gamma, p gamma, delta alpha beta, delta mu. So this is not really anything really new compared to this one, but there is the part, it's the anisotropic component of the active stress, which will be zeta, the alpha, the beta, delta mu. And this is probably the most important term in terms of active hydrodynamics.
Stress is appearing depending on the rate.
Because delta mu,
That's what you're going to generate.
okay, so the delta mu would generate the rate in ATP hydrolysis. So that's the first, and then indirectly
There's going to be
there's-
another equation.
yeah, so there's an equation that would be R, which is then just the capital lambda delta mu. Things, right? On the same level, on the same level.
I don't.
No, it's R is the rate already. So R would be, so if I just look at the number of ATP molecules, the total number of ATP molecules, then it would be minus R. Because the number changes by the rate of ATP hydrolysis and it's reduced to this, but we have to minus sign.
Why isn't there a term that is simply PI for the data without data?
Because P alpha and P beta are not my forces. So I'm really expressing everything in terms of my forces. There are additional terms. And these are the ones where I couple the P, the alpha, the sigma alpha beta to H alpha. And so in principle, again, the system were isotropic, well, then it wouldn't be any H alpha, but then I couldn't, because obviously this is a tensor of rank 2, this is a vector, so I could not. But now I can do this and put in here P alpha, H beta, plus P beta, H alpha, which is one, and let me just check for the signs, just to make that as a one.
What's the second term that from zeta bar?
Oh, that's just because I have here a term that has P alpha, P beta, And there's another one I can form just for completeness. And
That's P gamma, P gamma.
that's P gamma, sorry, yes. Please, very well.
Which is as the level of the guitar. So,
Yes, please.
so why are you not calling these terms C part of the stress tensor? You were saying there's the Ericsson stress tensor, and then these other pieces, including the bit you just written down, which by the way, a lot of the
Yes.
And I am used to thinking that would be part of sigma, but I think this is maybe just
Yes, so it
a
is.
notational rather than
So
conceptual
that's the
issue.
So that's the derivatory part of the stress that I've now, I mean, there's one more term.
Terms that you wrote down before, yeah.
But now I can, of course, write down the total stress, which
Okay.
has this component, so all this part is covered. It's just, this one is the, what I would call the active stress.
Yeah, but the one you just added,
And that,
that's part of the. stress.
so they, okay, so they, okay, so that's the thing I find the most annoying about non-equilibrium thermodynamics. That is that you have lots of freedom, but you do not have infinite freedom. That is. This way, writing down things involves some choices that I've made.
Okay.
And I could have made other choices. So for example, as I mentioned, I could have chosen the symmetric form of the question. Okay. Who tells me which choice is the right one?
So the important thing is the equations of motion.
The invocation of motion, they are all equivalent and they are in every way. Okay, so then there would be some alternative in view of the time I will not write down now. And you do the same thing for P alpha, where you can invoke the Onsager relation. So there are these cross coefficients. So you see this theta couples sigma to delta mu. There would be also the contribution to R coming from V alpha beta. And that would have the same coefficient in front of it. So I think I should stop here. There are a number of things I would still like to discuss, but I propose to do that on Thursday. So if you have now immediate questions, you can ask me now. I will put the full equations on the screen on Thursday so that you see them in full beauty or ugliness, whatever you want to call it. And with this, I think I stop for today.
We've got a limited time, it's about one of the questions, then we can discuss having over lunch.
Okay, well, this might be something to discuss with the next month, probably longer, but in trying to think about how to connect this up to microscopics, like, you know, actual eyes of force generation. I still find it confusing because presumably the active stress is going to come from some force generation applied. And that's not even monotonic in rates or concentration, let alone linear. So it's
Okay, so here in this linear approximation, theta is a constant. So what you do in order to describe these systems, what you will often do, you would have to add some linear term or some additional dependencies. And exactly one thing is to make these terms with not a. And that would,
I wonder if it's
so
yeah, somehow it's-
so what I would say for the time being, this is okay. Let's say semi-solid. In the sense of usual center of or non-equilibrium thermodynamic. And then you can make experiments to running that rates if you want. And there you're a little bit lost. I mean, you could again write down systematic terms, but then you have a collaboration of these coefficients that's just enormous, that does make sense. So then you want to have an idea of what are the most important terms.
But like I said, it's not even monotonic, let alone. So,
Well, you would see, I would be an example of normal all. Unless there's other things people would like to see, but.
Okay, so probably we will do the straw poll online.
Good. Yeah, okay, thanks.
So it's not straight. Then things like that. And then I would say it would be that next.
Okay,
But I think it's partly just the history.
yeah, so I guess, what we will start, I mean, Karsten, from your last lecture, what would be, I mean, I'm gonna just ask some people, but I mean, I guess what's your suggestion?
So my proposal would be to, well, first of all, before these trade ones will go, not on the backward anymore, then to talk about one effect that I think is the most striking effect of all this unique generation of spontaneous growth without any computation, just showing what people and